we were going through the commits. We were talking about GC objects.
Mhm.
What else happened there?
So we were visiting PyObject members and TP visit hooks, and after that let's see here. After that, in the original branch, there's a commit to use PyModule dev slot, which is already applied, and then using module state.
Yes.
Is there anything else we wanted to talk about, or do we go through this one?
Oh, we can go through this one, I think. I don't remember anything open from last time.
Okay, so let me check if this thing applies. Doesn't. There's RPM module clear. Oh, there's this add? No. Okay, so let's fix it up and look at the changes maybe. RPM module, let's see. Alright, so we had this in our branch. This was the original, and this one. So the change in the commit I cherry picked was from this to this. So it calls RPM module traverse, remembers its result, and then sets mod state to null. So that's kind of the original, and the cherry picked commit changes that to not set module state to null. Right?
Yeah, why is that?
So what is mod state?
Mod state is our structure we defined to hold the module state.
Mm-hmm.
And
So I'm not sure why this is done here, but so this will be a change that will take a few commits, and the main thing in this change, let's look at the GitHub. The main thing in this change is we're removing the malloc that sets the mod state.
yeah.
Right? So there was a malloc, an error check, and setting the mod state to all zeros.
Yeah.
That's now gone, and we're using the actual module state. right?
Mhm.
In the slots for the module, in the module definition, we're saying that the size, we're setting this M size to the size of RPM module state T, which is the type
Mhm.
of whatever mod state pointed to,
Mhm.
which means Python will allocate this much memory when it creates the module object, and that'll be available using this PyModule get state, right? So right now, after this commit, we will be using the module state instead of some global piece of memory somewhere. Well,
Mhm.
Instead of manually allocated memory. Originally it was global, now it's manually allocated. Now it will be the actual module state.
So PyModule getState is a function that is available to us via Python, and Python
Yes.
knows how to get the state because we defined the size.
Yes.
Okay, I get it.
So Python will reserve this much memory inside the module object for whatever we want to do with it, and then give that memory back once we ask for it.
Mm-hmm.
Right? To make everything work as it would before, this also sets the mod state pointer like before. So this is still a global pointer.
Mm-hmm.
So we still cannot have two RPM modules coexisting. So we'll want to get rid of that one after we do some more fixes.
Mm-hmm.
And it also says, if the mod state is not there, then we return -1. That's not very important because it can't really happen. If allocating the module was successful, then it needed to allocate this much memory. There's not much to that can go wrong there. And this commit also removes the setting the mod state to null when the module is cleared, which we'll need to do that eventually. This might not be the best time to do it, but we might as well do it now.
Mm-hmm.
Time as in, the series of the commits. So let's do that. So what this did is remove this mod state, and I see we also have a free here, which originally there was no free. We just leaked the memory because we know it's only allocated once. So we need to remove the free. We can remove the mod state equals null because we know nothing else can reuse that. Well, I still have the check where the module is only loaded once per process. So remove these two lines, and that means we can just return this one. Sure. And we have whatever was here before, but an added comment, and the comment is still valid. So that's the version I'm going with.
Mm-hmm.
Now for free, it's the same thing. There was a free here, which we eventually will not want. There's a mod state equals null, which we'll eventually want to get rid of. And there's checking this mod state. How does this work? Wait, does RPM module, does PyModule def free, whoops. I had the tab open in a different, that's free. shouldn't get the state, but the module object. So this state was misleading, I think. Is it? Really fix the documentation here. Let's see how is this used in CPython? Module free in C types. It gets the module. I don't know why we had this state argument here. Threw me off. It doesn't make much sense. So we're getting the module. So no null here. Again, we don't need to state set module state to null. We don't really need to look at mod state, the global variable, at all. So no if. So we're keeping this free like this, right?
Yeah.
And we do the same thing as traverse, or the same thing as clear, which sets everything to null and destroys references. So the only difference between clear and free is this return. When we're freeing stuff, we ignore all errors because there's nothing we can do about errors. Next change. Whoa, this is big. So init RPM. Apparently this gets rid of the check that we can load the module once per process. This malloc, no, wait, this adds it. What did this commit do? Oh, the commit removed a line here and removed the malloc.
Yeah, we have the check like this set string function already in a different function. We don't have it.
Right. Yeah, so yeah, the commit removed this malloc. So we need. So let me check what this commit actually did. Yeah, remove the malloc, and we need to look for the malloc somewhere else and remove it. It's an init module right here. Okay. Okay, and then it sets mod state using PyModule get state. That's already here. All right. Let's see if that still works. No.
No.
It does not work at all. I think I saw an error somewhere here. Oh, that's just a settings warning. Okay. Let's look at the diff. The diff looks rather good for a merge. So what's wrong? there are some failures. That's 128 failed. How did it fail? Exit code was 139. Well, great.
We have seen that one last time.
Something's wrong.
Segmentation fault, core damped.
Oh, do you see that somewhere?
Yes, on the line 29.
Ah, great. Okay. Did we manage to get GDB running on this?
Yes.
Oh, that was make something else, right?
Eggshell or shell?
Make shell? Ah. But we don't have GDB.
But we should. So we updated the Docker file to. But we probably did not commit that.
I didn't commit that. So do it again. Where is that? Tests, Python, tests, Docker file, Fedora, GDB. Hopefully that's the correct one. I wonder what this number refers to and how old that is.
Yeah.
Alright, we have GDB and we want to run with args and something that failed. Args and Python, right? Search file or directory, Python 3. Okay. Run. Import. Importing looks like it works. This DB path looks like we don't want that. DB format is not there, my print is useless. So this makes a TS, sets some flags, makes a pool, does stuff, prints stuff, prints stuff in a loop. So far so good. And exits normally. So what's the problem here? We have Python debug now. And are all of these segfaults?
Yes.
Yes. So let's look at the diff once again. What could go wrong here? Oh wait. This isn't cherry picked properly. This is missing a crucial part. This is missing the setting the mod state.
Didn't we have that?
Got rid of the malloc? No, so this should be an init module right before setting PyRPM error. Let's see. Oh, it is there. Was it there already? Did I just miss it? Oh, I already had that. So, okay, so if I go to the shell and run Python, so how is the Python run here? Put something at testpy and then runs Python on testpy. So let's do it like that. Oh, there we go. Add macro argument 2 must be string, not none. That's because we don't have DB format. I don't know what DB format should be. Oh, there we go. There's a segmentation fault. And if we run GDB, there's a segmentation fault. Nice. Okay. I wonder why this didn't happen before. So what do we do with a segmentation fault? We can look at the backtrace, and there is a backtrace coming from finalize modules, git collect main, type clear, tuple dealloc, pyobject gc del, and free. Huh. So this is failing on deallocating a tuple object. We don't have any debug information here for some reason, so we can't tell where the tuple object is coming from, but something is wrong.
We can install into the environment Python free debug and debug info packages, maybe?
Yeah,
helps us more.
Probably be better to run this with
internet
access, but yeah, we can put in how do you do that? That's DNF debug info. That's probably some part of DNF that isn't normally installed, right? Debug debug info install plugin package. Okay. Let's try that.
Will that command work? It won't. There's DNF.
Try DNF install. Oh, DNF. Ah. Ha!
Wow, I didn't know that. I was installing the exact packages when I needed them.
Yeah, the exact packages change every time, right?
Yes.
Yeah. Okay, so now we need to again export DB format. Wait, how is it remembering my batch history? It's interesting. Okay, so cat this to test.py, gdb run test.py, and there's debug info.
Oh. This is more.
So we go up to PyObject free. Oh, pointer is already optimized out. Everything's optimized out here. We don't have this op. No frame has this op. There's a tuple. Ah!
What does it mean optimized out?
So when you debug a Python program, you always get all the variables set exactly as you have it in the source code, right?
Mm-hmm.
Which is actually a pretty good feature of Python because it's debuggable easily. But in C you have a compiler, so it can see that, I don't know, there's a release level variable here, and it's used up to here. So the compiler builds the argument list for pyargparsetuple and then forgets release level, and maybe it puts something else in the place where release level used to be. So once pyargparsetuple is called, the debugger cannot see release level anymore. It's been optimized out. There's a way to prevent this. If somehow we can pass compiler flags to the build, you could put -0 for don't optimize, but this goes through Docker and CMake, so I have no idea where to put that. But I guess here I has been optimized out. Maybe it's 0 already. There's a type. So there's a variable of type. What's that? Object 0. Oh, there's a very high reference count. If I print /x for hexadecimal, I see the reference count has a very interesting value. And then at position 3 in this tuple, there's a null pointer. I wonder how so OP is a tuple. How do we know that? Well, I guess that's the tuple dialog. So OP is defined as a tuple object. And if I do print OP arrow and tab, it gives me all the fields of the tuple object. One is OB base, which is pyvar object. One is OB item, which is the array of pointers to the contents. So if I look at the OB base,
the size.
It gives me the size. So this tuple has 2 types in it. And OB base is the Python, is the Py object. So there's the type, that's tuple, and ref count is 0 because we're deallocating the tuple. Alright, so there's this type and that type. There's 2 types here. This is probably, I mean, from the looks of it, this tuple was probably used in the MRO, in the list of superclasses of something. So this object is immortal, probably, has a very high reference count, and this object now has a reference count of 0 because the tuple just did a decref, so this object is being deallocated. Let's look at what these types are, right? So this is, so there's inside the tuple, so they're arbitrary Py objects, but here we know the type, so we can cast this this thing to a Py type object and get back the contents.
Wow.
And apparently something went wrong there. So this is the Py type object, which has an OB base. That's what we saw before. Oh, it also has OB size. It has a name, and we can see that this name is not great. If we look at the other one, the name is object, right? So this tuple, that's more confirmation that this was an MRO. Ends with object, but the subclass here has some garbage for the type name. And yeah, it has a ref count of 0, so it was probably deallocated already. So we could use some tool to see what this was, but it's probably something in our code, right? And the types where something could go wrong are all added here. So I wonder where the ref counting can go wrong. Like, to avoid this, we could do something like avoid clearing things. If I comment this out, everything passes. But it also means we hold on to references to those types, so that will leak memory. We're not doing the reference counting correctly. We're letting things live, and they shouldn't. So, okay, let me see the history here. If there's anything I've solved before, no, so this needs to be solved again. All right. Why does this fail? So this will add types, and it should make the type with by type from spec, and it does PyModule add object. PyModule add object is a bit weird, as the comment says. So it will steal a reference to the type on success. On error, it will keep the reference, right? So what do we do if there's failure? We get rid of our reference because we don't need the type anymore, and we return 0. Okay. So init add type. If that doesn't succeed, we -1. So the reference is stolen, and it's given to the module. By module add object. And this is set to the new type, right? So the address of this is given to the function. So this is PyType object star star. So we get the pointer to something we should fill with a pointer, and right. So this this adds a new reference here, and this gives that reference to the module, right? So we're storing the type object in two places. Once in the module dict, so it's accessible from Python code as an attribute on the module, and once inside the module state, so that we don't have to go through the attribute access, which the user has access to, so they can remove the type or change it to something else. So when we want the type from C code, we want to go through the module state, where we know we have the object that we put there, right? But this this function is creating a reference. This function is stealing that reference from us and giving it to the module. And we also have an incref here. So this makes one reference, this makes a second reference, and this steals a reference from us, so we're left with one reference, which is correct, as far as I can see. And we need to get rid of that reference, and we're getting rid of that in here. With the clear, which does clear. And clear will remove the reference and set the pointer to null. And there is the problem. This is being too smart for its own good. I see it now. and that has to do with pointers. Okay, so what PyClear does, so let's look at the documentation. Maybe it's clear. So this is a macro where it takes a pointer to an object. It will destroy the reference and set the pointer to null. Right? So that pointer can't be used again. It's like a marker that this reference was cleared, right? So we do that here in clear, and we do that here in free, right? So Python can call clear and free when it's removing the module. It calls clear to get rid of all the references, and then it calls free to before it deallocates the memory, right? So what we want to do here is here to release all the references and set all of these to null. And here, well, in case Python didn't call the clear function or something went wrong, we want to do that again. Now if clear sees a null, it'll do nothing. Right? If it's already null, it'll do nothing. So that's why we can do this 2 times. Right? And nothing should happen. But the problem is the PyClear does not set the correct pointer to null. Because this clear gets a PyObject argument. The clear sets that argument to null, but it doesn't set this. It doesn't set the module state to null. Does that make sense? If it does, you understand pointers now. So we actually need to do this whole thing in here.
Okay.
Well, what was the return? The return was the same. Right? No fancy stuff with the clear, and we do this here. Okay. Hopefully that'll that'll work. So what I've done here is now I'm actually using clear on the pointer that I want to set to null, so that when it's done again, PyClear will see the nulls and won't do the decref again. One more thing, this void here. I've started doing that quite recently because something started adding a warning about ignoring the return value from a function, where this RPM module clear returns an error message or an error indicator, basically, and I want to explicitly ignore that. So I do that by casting to void, which does nothing, but it tells the linter to shut up. And there we go. Okay.
Oh,
We got rid of a bit of magic at the cost of some code duplication. But yeah, we're good now. And I should amend that. So, you said everything made sense, which is great. That means you do understand pointers and you're a C programmer now. I
need to take a look at this diff again.
Okay. I'll push it. So that was this use module state, right?
Mm-hmm.
Okay, next up, add mod state declaration to individual files. So what is this one doing? It is adding a mod state declaration to every C file and hopefully removing it from the H file. So what we want to do now, the module state is currently accessible in two ways. It's accessible by PyModule getState, and it's accessible by the global pointer. And we want to get rid of this way of accessing it, right? That's too much to do at once. So what I'm doing here is removing the definition wherever it's defined. Oh, header, that's RPM system probably. This one, that's getting removed. And of course, if I remove it, I will get a compiler error at every point that wants to access that. Right? That's a lot of compiler errors. And I don't want to fix them all at once. So I add this to every C file that needs it. And then I can go individually through each C file, remove the declaration, and see the errors only from that file.
Okay.
Right? Okay, so let's cherry pick that. Okay. Good. All right, and then this bumps the minimum Python version to 3.10 without any explanation. It's probably something is using some function that was new in 3.10, and I don't know what that is. Was it PyModule getState? No. I don't know. Should probably test it with 3.10 afterwards.
Yeah, was it like slot declaration, maybe? You all made it before? No.
I don't know. Can we try compiling with Python 3.10? This is supposed to be using the limited API somewhere. 3.7. So the API should be compatible with 3.7, but there might be some behavior change. Let's see. With Python 3.7, will that be enough?
I'm not sure there is Python 3.7 in Fedora 41.
Ah, we need 3.6, right? Oh, 3.8.
3.8.
But maybe something will still install the newest one. no Python 3.8 devel. Oh, is it a single package?
Yeah, it should be. Fedora 41 still should have it.
But it's installing Python 3 libs. Well, maybe not Python 3 devel. Ah, everything failed. Everything failed?
Oh, it tries to use user bin Python 3.13 on line 40. You can see.
Oh, how do you see that?
Yeah.
Okay, so we also put 3.8 in here, right?
No, not less than.
Your what?
Not less than.
Oh, right. So yeah.
Yeah.
Oh, still work. That works.
Okay.
Did it use Python 3.8?
We can take a look at the test that keeps failing. There will be a log probably.
Oh, 136.
Maybe it will.
Yeah.
Does something? No, it doesn't. I hoped it could resolve the variable.
Well, it didn't find the module interpreter, so it's not 3.13. Success.
Interpreters are a 3.13 feature.
I don't know where it got added, but it didn't fail this way before, so it's a different Python version, and it's probably 3.8 then. Alright, so let's revert that. 3devel. Oh, did I check in the Docker file change? Ah. Okay, I'll need to redo that. This one. Undo that Docker file change. Let's restore from the previous commit. Source is the previous commit file name. No. Oh, I'm in a different directory too. Okay, so now that only has changes to the code, right? Yeah, the test infrastructure changes should probably go in a separate temporary commit or something like that. Okay, so not yet. Maybe the next thing we'll need it. Oh, this one. PyType from module and spec. Let's see. That's the one.
Mm-hmm.
That's the one. Associate the module with the types. Okay. So this will become clear in the next commit. Add accessors for the module state. So it's probably better to work backwards here. So let's do this. Get the state in header py.c. So this is the commit that we want to get in, removing the mod state here, right? So if I do that in header py.c, I will get my compiler warnings. Make and that'll say mod state undeclared, right? So I need to get the mod state from somewhere, right? Now I'm in this function, hdr as bytes. That's getting some kind of header object. So that's a Python wrapper for an RPM header, and that's all I want, all I have, right? I have global state, and I have this object. So I obviously cannot go from global state to the module state because there can be multiple module objects. So I need to work with this thing. And I know S is a type I'm in control of, so I can get the type of S and get to the module from that, right? In order to get from the type to its module, I need that link to exist. And the way to do that was, unfortunately, added in 3.9. Right? So before that, there was PyType from spec with bases. Before that, there was PyType from spec that takes a type specification and gives you a Python type object. This one does the same thing, but you can pass in the bases, like the base types. So that's not really relevant for us. This one is the same, except now you can add this module, which gets stored on the type, and then you can get it back. Right? After that, we added PyType from meta class, which has one more argument. And anytime you know there's a new argument to put in, there's a new function for it. So these all say equivalent to the new one, equivalent to the new one, equivalent to the new one, so they all have the change logs. So this one says anything you want to know about the module. The module argument can be used to record the module in which this new class is defined. That's exactly what we want. Must be module object or null. If not null, the module can be retrieved by PyType get module. And well, we also added in 3.9. So this was added in 3.9, but it's only part of the stable ABI since 3.10. So that is where the minimum version comes from. Without this, things would be very complicated. Okay, so there's PyType get module. There's also a PyType get module by def, which is new in 3.13 and is even more. It's even nicer. So this is why we have these commits here, right? So instead of PyType from spec, we do PyType from module and spec. For that, we need to bump the minimum version, the limit API, and find package. On 310. And with that, so this is RPM mod state from object, and that's a helper we'll also need to add, and that'll use the PyType get module. But we're already over time, so we'll look at that next time.
All right.
I see this steals get module PyType from 311.
Wow. Okay. Right.
All right, so see you next week.
See you then.